Hi everyone, today we're going to talk about topic 8.7, pH and pKa of salts. And so to get started, I want us to kind of look at this trend and think about a way we can explain it. We have unboiled water that has some CO2 in it. Its pH is less than 7, and so it's kind of acidic. If you have boiled water, which is just water, it's neutral, of course, because there's nothing else in it. If you dissolve NaCl, you get an acidic solution. If you dissolve acetate, this is acetate anion, we'll get a basic solution. If we dissolve NH4+, we get acidic. This zinc salt here, which is a cation, is also acidic. An aluminum cation is also acidic. And then finally, CO3 2-, which is carbonate. This is basic. And so if we look here, we can generally say two things. Dissolved cations equal acidic. Right, and that's what we see. NH4+, 4.4. ZnH2O6, 2+, 4.4. AlH2O6, 3+, 3.8. And dissolved anions equal a basic solution. I'll explain this more in the following slides, but that's generally the trend that we're seeing here. So when we think of the acid-base properties of salts, what we need to keep in mind is that ions can react with water to form H+ and OH-. And so we're not necessarily thinking about acids or bases here. We're thinking about ions that can react with water itself to form H+ or OH-. This reaction we call hydrolysis. Or in other words, we're hydrolyzing the salt. And so we'll take the acetate anion, for example, C2H3O2-. If you react this with water, this will be aqueous, this will be liquid. What will happen here is the acetate can take a proton away from the water. We get C2H3OH and OH-. This, of course, is acetic acid. And because of this, your pH will go up. And so the water reacted with the salt to make a basic solution. And to determine if a salt is an acid or a base, you need to look at the cation and anion separately. Cations, or positively charged, those can be acidic or neutral. The anion, which is the negative charge, can be acidic, basic, or neutral. And we'll go over both of these cases now. So let's take the case of anions first. These are negatively charged ions. Anions of strong acids are always neutral. So you got to remember your strong acids. If you take away the H from the strong acid, you'll get an anion. So Cl- is neutral, Br- is neutral, SO4 2-, NO3-, ClO4-, ClO3-, and I-. Right, all of those are the reaction of a strong acid with water. You'll get H+, which of course is acidic, and I-, and some sort of anion afterwards. If you add that to water, the solution is still going to be neutral. The next one is anions of weak acids are conjugate bases, and they'll produce OH- in water. And so I already gave this example on the last slide, but if we have C2H3O2-, if you add this to water, it's under equilibrium, we'll get HC2H3O2 plus OH-. And because we make OH-, this will make it basic. The last case is protonated anions of polyprotic acids. Again, polyprotic, meaning more than one proton. So an example of this is phosphoric acid, which is H3PO4. Since H3PO4 has 3 protons, we'll have 3 forms here. We have, right, the neutral form, which is the regular acid. We have H2PO4 minus. We have HPO4 2 minus. And we have PO4 3 minus. And the rule for something like this is if Ka is greater than Kb for the ion, the anion is acidic. And the opposite is true. If Ka is less than Kb for the ion, the anion is basic. Which makes sense, right? If Kb is larger, then that means it prefers to go in the direction that makes OH minus instead of H plus. Now looking at it from the cation side, things are a little bit more simple. Group 1 and Group 2 metal cations are neutral. Group 1 and Group 2 are essentially, this is my little periodic table, this is Group 1, and this is Group 2. And so these are basically the product of strong bases. Right, the cations that are made from strong bases, those are going to be neutral if you add them to water. Polyatomic cations are typically the conjugate acids of a weak base. And so what this essentially means is something like NH4 plus, right? Polyatomic cation, it is the conjugate acid of a weak base. And those are typically acidic. Last point here is that transition and post-transition metal cations are acidic. And so here, by transition metal, it essentially means this block. And post-transition metal are the metals right after. And so, for example, like Zn2 plus, right? Zinc is right about there. And so this would be considered acidic. Now, the reason you might be confused as to why Zn2 plus itself would be acidic, the reason why is because something that we've kind of looked at before, which is water of hydration. Essentially, if you have a metal cation, like a post-transitional metal cation or a transition metal cation, what happens is water attaches to it, like you see in this diagram here, and if another molecule of water approaches it, it'll essentially take one of the protons because this proton on the water that is now bound to the metal is slightly acidic. And so you're left with this new kind of hydrated metal where you have 5 waters and then 1 OH now, and then this is H3O plus. And so transition and post-transition metal cations, you add them to water, they're slightly acidic. And so here's just kind of a giant summary table of what to expect here. Group 1 and Group 2 metal cations with anion of a strong acid are neutral. Essentially, the product of a strong acid and strong base equals neutral. So NaCl, for example, I get that from mixing NaOH, a strong base, and HCl, a strong acid. And so NaCl, this will, in water, is neutral as a result. And so the product of a strong acid, strong base reaction will make a neutral salt at the end. Group 1 and Group 2 metal cations, in other words, the product of a strong base with the anion of a weak acid, will be basic. And so this, for example, is, let's say I take NaOH and I add it to, let's say, formic acid. This is a strong base. This is a weak acid. Its product is going to be essentially COO, well, HCOO minus plus water. Right, at the end of the day, we technically have Na as well, and we have Na over here. And so I'm not going to necessarily count the Na, but this anion, this HCOO minus, this is slightly basic as a result. So if you react a strong base with a weak acid, the conjugate base that you get will make, if I dissolve in water, this conjugate base will make the water basic. So if I react a strong base and weak acid together, that conjugate base that I get, if I take that out and put it back into pure water, it's going to raise the pH. Now let's look at this next case. Transition and post-transition metal cations, and this should say or polyatomic cation with the anion of a strong acid is acidic, like the cation. I know this is very confusing, but I'll give you an example here. So if you look here, we're given ZnCl2. You get ZnCl2 by mixing, for example, zinc hydroxide. This is a weak base with HCl, a strong acid. So this is the exact opposite case of what we're talking about in point number 2 here. What we'll get is we'll get H2O, because the H will mix with the H2O, and you get ZnCl2. The cation here, this Zn2+, this is an acidic cation because it came from a strong acid and weak base. And so the point I'm trying to get across here is if I do a reaction with a strong acid and strong base, the salt that I get isn't going to change the pH of water if I add that salt in the water. But depending on if I get a salt from either a strong base with a weak acid or a strong acid with a weak base, the resulting salt will make the water acidic or basic depending on the one that is strong. The strong one always dominates. The last case here, and again, you should refer back to this if you're doing practice problems and find that you're confused on which salts are going to make water acidic or basic, refer back to this summary. But transition or post-transition metal cations or polyatomic cation with an anion of a weak acid, in other words, a weak acid, the product of a weak acid plus a weak base, and this weak base is going to either be a metal or polyatomic. Whether or not it makes the water acidic or basic depends on Ka and Kb. We won't see many examples like this, but basically for this case, if it's weak acid, the product of a weak acid, weak base, the salt acidity or basicity depends on if Ka or Kb is larger. And that's essentially the different cases that we're going to have here, right? The product of a strong acid, strong base, the salt is going to be neutral. Product of a strong base, weak acid, the salt that it makes is going to be basic. The product of a strong acid and weak base, the salt product is going to be acidic. And if it's weak acid and weak base, that salt that you make at the end, it's going to depend on which one has the higher Ka or Kb. So here's a table to kind of illustrate my point. Let's look at a few of these. NH4NO3 or ammonium nitrate. NH4, I get that from NH3, which is a weak base. NO3, I get that from HNO3, which is a strong acid. Since this salt is the product of a strong acid and weak base, its pH should be slightly acidic, and you see here, it's slightly lower. Let's take sodium chloride. Na, you get from NaOH, a strong base. Cl, we get from HCl, a strong acid. And so, because they're both strong, that salt itself is a neutral salt. It will not change the pH of our solution. If you look here, sodium cyanide, Na comes from NaOH, a strong base, and Cn comes from HCN, a weak acid. And so its pH should be lower because the strong base is dominating. That's essentially what I'm trying to get across here. The salt that you make is going to be acidic or basic depending on the two things that make it. The last little point that I want to make in this little lecture is talking about indicators and thinking about titrations, because it kind of relates to the whole conversation about pH and pKa. And so indicators are typically weak acids that have a different color than their conjugate base form. In essence here, if I have HA, right, that's my weak acid and this is my indicator. Let's say before the reaction, it's red. I add it to some water. It's under equilibrium, and I end up getting this blue-colored A- plus H3O plus. That's essentially why you can use these indicators in titration, is because the color that it has when it has the proton on it is different than the color when it's in its conjugate base form. And so each indicator has its own pH range at which it'll change color, which is why you can't always use the same indicator for everything, and you have to be very careful with your choices. There are some questions on AP Classroom that expect you to know how to make these choices, and I'm going to show you an example in a second. And so an indicator can be used to find the equivalence point. Again, as a reminder, equivalence point is when number of moles of acid equals number of moles of base, as long as it changes color in the small volume change region where the pH rapidly changes. That is a confusing way to say, if I have a titration curve, your indicator should change color here, essentially in the range of the big jump. That's where your indicators change color. That's essentially what that sentence is trying to say, but in a kind of confusing way. And so in bold here, choose an indicator whose color changes at the equivalence point of your acid and base. The way to essentially know that is that the pKa of the indicator should be close to the pH at the equivalence point. Now, here, you don't need to remember this, obviously. Remember, for strong acid, strong base, the equivalence point is going to be at 7. For weak acid, strong base, the pH is going to be more than 7. For weak base, strong acid, the pH at equivalence will be less than 7. And typically, you'll have this giant indicator list here that you can use if you're working in a lab, and you can find which one works the best. Universal indicator is really good because you can see an entire range of things, but oftentimes people like using specific indicators. For example, if we take methyl orange, that works between 3 and 6, and so you'd use that for a weak base strong acid titration, for example. What we used for our lab was phenolphthalein. You can see this works essentially between 8 and 10, which is what you would use for a weak acid and a strong base. Okay, I want to go over this one practice problem before I end off this lecture. It says a student pours a 10 milliliter sample of a solution containing HC2H3O2, also known as acetic acid, which is a weak acid, has pKa of 4.8. And as a reminder too, pKa just equals minus log Ka. If you're ever given a pKa or Ka, it's usually weak, or at least in this class, it'll always be weak, with NaC2H3O2. Now, as a reminder, this, right, Na, we get that from NaOH, and this we get from acetic acid. And so this is the product of a weak acid and a strong base. So as they put them in a test tube, they add a few drops of bromokisol green to the test tube, and they see a yellow color. And so that indicates that they tell you that indicates that the solution is less than 3.8, or at least the pH of the solution is less than 3.8. So based on these results, which of the following must be true? It says either the concentration of weak acid is stronger than the concentration of conjugate base, that they're equal to each other, that the weak acid is less, or that you can't determine it without knowing the value of pKb for C2H3O2. I'll tell you, this doesn't really matter because you can always calculate it. You can always calculate pKb because remember, Ka times Kb equals Kw. And so, and we know this number, and it should be on your reference sheet. So you don't ever, that can't be the answer. If we look here, our pKa is at 4.8, and you notice the pH is less than the pKa, suggesting that it's pretty acidic. And so the most likely answer here is that we have excess acid in solution. Bromocresol green also works in acidic conditions. And so it works in acidic conditions. You're in a slightly acidic solution. Your pKa is higher than your pH. That should mean that I have more acid than base. And so if we think about this in terms of titration, I'm adding NaOH to it, which is essentially what I determined here, right? NaC2H3O2 is from NaOH. Acetic acid is the weak acid we're titrating. We're essentially, I'll write this in blue, we're at this point in the titration curve. We haven't quite jumped up yet. And so that's how you'd approach a problem like this. You'd look at what the pKa is. You'd see what you have there as well as how you made the salt. You would look at what your pH is and then think about which one must be true. Since you have a low pH, you must have more acid than base. We'll go over some more problems in class, but for now, that's all. Thanks, guys.